Everyone, I am Mustafa and today I am going to present our introduction to machine learning class final project that is completed me and my friend Muhammed Ali Ünal. Our project topic is phishing, phishing attacks. To implement this project, we used different machine learning algorithms, and some of them is from scratch, and some of them is with pre-built libraries. Let me show you the project first. I am starting Jupyter Notebook in the directory. As you can see here, we have 6 different Jupyter Notebook files. 2 of them, as you see, progress presentation Jupyter Notebook files is all files. We actually for 4 Jupyter Notebooks for this project. First of all, data process IPython. We have used 2 data sets for this project, and one of them is Kaggle website, and the other one is collected from the actual real world environment. Real world environment network dataset, and here data.csv, as you can see. But there is some problem. we need to find a different way to simulate phishing attacks in a normal neural network traffic. In a real environment network traffic. Here we processing the raw network data, and we labeling the data as suspicious or not, as 0 or 1, as you can see here. In this code I am actually very basic steps. First of all, I am identifying the risky ports, and I am labeling, first of all, the rows, samples, according to these risky ports and some registered ports. After that, I am going back to IP columns of data, and I am reshaping the data according to the IPs and relabeling or labeling again the data. And this after these operations, we have 39k normal traffic and 13k suspicious traffic, is labeled 0 or 1. After that, I am going to neural network.ipython. We implement a neural network, artificial neural network from scratch. We getting the data cleaning, pre-processing here, train X, train Y, separate data. And here is our neural network. We have 4 layers here. Each layers consists of these neurons: 15, 10, 5, 2. And here is our units weights function. In this class, we initializing weights for these layers and neuron size accordingly, corresponding to layer size. And here are activation functions. Activations. And activations functions derivatives. Actually, you don't see softmax here because we combine the softmax outputs with binary loss cross entropy. And for each layer, we coded differently each layer's outputs and inputs and activations. We could use a for loop here, but for simplicity, we code it separately. And here our loss function. Actually, what I am returning here is that binary loss function, binary cross entropy. Of course, you can use different loss functions. You can try it yourself. After that loss functions, next comes calculate accuracy function. Calculate accuracy function is doing one thing actually. He takes the maximum of softmax outputs and match it with true label. If it's true, it takes the mean according to sample size and return accuracy. And next comes backward function. This function does backward propagation. He takes softmax outputs and get true values. Here is our softmax combined loss functions. We basically index of true value subtract 1. That's our loss derivative. And we divide it by sample size. And after that, we are going layer by layer. Error calculation, as you can see, error calculation, and here our gradients, our weights actually. Then I am returning these values as gradients to optimize later the gradients. Next comes optimize function. Optimize function is simple stochastic gradient descent. It takes gradients, learning rate, and decay, and iteration by iteration, decreasing the weights, layer weights. And here our fit function. Basically, it takes three inputs parameters: train X, train Y, batch size. Firstly, I am dividing the data batch size according to batch size. Let's say 20 by 20. Then I am calculating forward output loss accuracy and gradients for each epoch. After that, our prediction function comes. Prediction function simply forward the input data once and takes the outputs. And lastly, our pilot loss functions. Okay, let's see some results. Sorry. Why aren't you going to work? Label it data.csv. Let's go label it data. data. There's something wrong. Here. And here our loss functions. Sorry, gradient descent, loss and accuracy. In the training steps, I am getting 19% accuracy. Sorry, 90% accuracy and 0.39 loss value. And in the test set, I am getting 0.75 accuracy value. Loss is a little bigger, but is not important. This is our first from scratch code. Next comes linear regression with neural network. Let's open that. And here our another neural network. As you can see, let me write it down. Linear regression formula is y equals m multiply x plus bias. And actually, in the loss function, let's remind the MS loss function. Y subtract y hat power 2 for each elements plus sample size. That's the loss function. And if you take derivative with respect to m, you will see something 2 over n multiply some operation negative x multiply y subtract mx plus bias. And according to this derivative, I can find gradient value and update that gradient value. First of all, in init function, I am assigning learning rate epochs and create a list self.losses. Next comes init underscore params. Init params does two things actually. One is define the coefficient and slope variables, and next identify the weights according to features, not samples, not sample size, according to the features. And here you can see, let's see an example how these are related to features. These are your samples, and in a matrix form, every column must be equal. Sorry. Each row is your sample, and in each row, in 3 value is your features. I have 3 sample with three features. And here self.w equals mp.zeros is your weights according to the features. After that function, forward function comes. Forward function just working just a neural network forward. It takes input, multiply it by weights, and plus bias. And here our loss function comes. As we defined earlier, you can take derivative of loss function to combine weights to update weights. Here are calculated accuracy function. And here our backwards function finally. I am taking the prediction values here and true values. And I am updating weights according to the derivative formula and biases. And here our fit function. This fit function takes data into the batch, separates data into the batch data, and goes over these batch datas. Here, for epoch in range self.epochs, he goes over, he goes along to size of batch data and is doing that for 2 minutes, 2 times with this for loop. And lastly, our loss function, pilot loss function and predict function. Let's see some results. In this Scratch code, we use the first dataset, not the same dataset from the previous Scratch code. And here you can see my accuracy is 0.75 and loss 0.99. And here you can see loss graphs. It's decreasing, but very slowly. And my data is here very limited. And of course, we are coding it from scratch, not the professional ones, just an experimental work. We can do a lot of things to get these results better, like optimizers, loss value manipulation, backward manipulation, or initial weights of our one neuron's weights. Of course, you can try it too with the files that shared. After that, our last Scratch code, KNN algorithm from Scratch. Okay. In this Scratch code example, I will go step by step. Firstly, I am calling my fit function of my class. It takes 3 parameters: neighbor size, x, and y. It assigns train and train x and train y value and neighbors. Then it calls prediction method. In prediction method, I am calculating for a row distance of all the other samples. distance of a row or distance of a sample, distance of a test sample of all other dataset samples. And I am doing it in find neighbors function. Let's go that. In find neighbors functions, I am finding the distance between that specific data point and whole other dataset samples. I am appending it to a list, vector distances. Then I am searching that list according to distance vector, distance value from smallest to biggest. Then I am traversing a for loop for this neighbor size. In my case, I am going back 3 times. I am looping back 3 times. And I am finding the smallest vector distance values with vectors. After finding that, I am appending to a neighbor list. I am doing this 3 times, length of this neighbor's size, and I am returning the neighbor list. Then I am going back to prediction function, and I am taking the neighbor list and send it to another function, find label. In find label function, I am basically taking the maximum of output value 0, 1 or 3. Which one is maximum? That is my label. If there are 2, then I am calculating a set operation here. This is NumPy's native functions, and I am finding the label, return the label. And one more thing, in find neighbors function, finding distance with Euclidean distance calculation. I am taking all the features of one point and subtracted the other ones, and taking the power of these points, each one of them, by 2, and summing up all them. And finally, I am taking the square root of that value. That gives me one value for 2 points, for 2 data points. Then I am appending the label value, a list, prediction list. Then I am taking that test x value, I am taking its labels and compare it to prediction values. Then I am taking the mean of that value and finding the accuracy. And lastly, I am pinning down to accuracy. And let's try it. Let's wait a little bit. I am using GPU because of the dataset size and calculation operators taking too long. And here I am taking 500 examples, and model gives me 0.99 accuracy, and prebuilt library gives me 1.0 accuracy. And that's our project. Of course, we try another methods, SVM, random forest, one of naive bias, but we try them with prevalent libraries. We just coded 3 algorithms from scratch: KNN, linear regression with a neural network, and a neural network from scratch. And I want to thank you, our instructor, Duygu Sarıkaya. Thanks. Goodbye.